Hello, everyone. Good morning, good afternoon, good evening, depending on where you are. I assume most of you are in Israel, Tel Aviv area. My name is Yogesh Bhatt, and I'm going to talk about impact of AI ML on next generation communication systems. I am basically working with Ericsson in Silicon Valley office, and this is the work we have been doing here for about past 3 years. And I'm going to share about our learnings and experiences here. So let's jump right into it. So here is the bird's eye view of the presentation. So essentially, next generation communication is impacted in two ways. First, the emerging AI ML enabled applications are really creating new demands on the next generation communication systems. And ironically, the AI/ML itself will be required to really solve some of those challenges. So here, as you can see, I will start out describing those new applications and services, which creates more stringent requirements on communication systems, because these applications are mostly in intelligent automation of different industries and different parts of our economies. And those new requirements creates such complexity that cannot be easily automated away by using the current status quo technologies and practices. And that requires us to again look at AI/ML itself to solve some of those problems. While that is all understood until now, what is the new revelation is that we identified that traditional way of applying AI/ML to systems area is really a non-starter to solve uh, the causality, which is key for trustworthy AI applications. So at the end of this presentation, I hope you have a great idea about how AI/ML is going to impact next generation communication in both the ways as I explained. So briefly, before we jump into the presentation, here is a brief introduction about myself. I have spent more than 2 decades innovating in mobile internet space, and my claim to fame was redesigning AT&T network for early iPhones and iPad releases. I have about 13 productized patents, and my unique ability is to really de-hype all these uh, hyped up technologies and try to identify what real business problems they can help us solve, and then pursue those solutions with entrepreneurial zeal. As I briefly mentioned, I am working with Ericsson for about past 8 years, and over last 3 years, I have been focusing on enabling intelligent telco automation. And I'm based in Ericsson's Silicon Valley campus and part of the Ericsson's Global AI Accelerator team. So again, welcome to this session, and let's jump into it. So, as I mentioned, that what are the new emerging application patterns that is creating that is going to show up over next decade or two, and what the real requirements it creates for next generation communication systems. So, as you see here, I have listed different app patterns or emerging application patterns, and then how each application pattern is architected today across the east-west side, meaning that from device to the server. And as you see, the smart, autonomous, and immersive, all these three application patterns are simultaneously evolving, and there is a lot of changes going on from cloud native. We came from cloud native to now most of the changes happening in the devices. So most of the cloud loads, as you see today, are like basically put on the user interface front ends are put on the public clouds because they can easily adapt to from touch interfaces to voice interfaces and then moving forward maybe to neural interfaces in the future. and but the main data is still sitting in the on-prem data centers or IT's own data centers. While if you see the autonomous application pattern, sensing and acting is obviously going to happen much closer. And now the cognition part of it is also moving towards the on-prem or devices, or basically moving away from global centralized distribution slowly. While the immersive media is happening, interestingly, that media processing is today happening mostly on the devices, but now we may need to offload it to make it more elaborate, and that then connects back with the smartness. So these application patterns are not distinct. Uh, Many of the services and applications will have one or more, and in extreme cases, they may have all three. But what this creates is that communication and compute infrastructure will have very different requirements than what we have today. So what I meant is that if you look at these different uh, use cases or business cases here, from real-time media to remote control and industrial control to mobility automation in different industries, as I have listed here on the right side, these new application patterns and their deployment scenarios will also vary very widely. So as you can see here, there are like a local area versus confined wide area versus general wide area, meaning that many of these applications geographical scope and as a result, the administrative and ownership scope will vary greatly. So meaning that the current architecture of device to cloud and then moving some of those cloud services, public cloud service to the edge, wherever that edge may be, it's a carrier edge, it's like metro edge, or then devices itself or on-prem, that the permutation and combinations of all those administrative domains, compute, security, communications, will create so many different options that it will become very complex when very fast. So how do we really manage and operate this kind of software and services, given that there are so many moving parts and so many variations? So basically, this kind of complexity traditionally has been managed by really humans collecting, analyzing the lot of data from different sources, as you can see here. And then they try to come up with the remedial actions or optimization solutions. And those course of actions are verified in the test devices in the real-time network. And then those remedies are applied. So the way we are doing today, everything manually is trustworthy, but it is not scalable. So, meaning that if you look at all the data sources here, this is, I'm trying to describe the now communication service providers systems here. And as you see on the periphery of this sphere are all the various data sources they have. And these data sources are really scalable on their own, but they are really sparse. And many of the like O&M and logs and other data, like system monitoring and observability data, are all collected over an interval of a few minutes to an hour, depending on the communication systems we are talking about. In radio access network specifically, it is 15 minutes. In transport and other data center networks in the cloud, there varies a lot. So when we try to manage and operate, first we need is a visibility. And this is not simple visibility, as it says that can machines see same things as humans do? What I meant is that if we apply the traditional human-led, non-automated way of operating and maintaining these systems, it would become too slow and it would become too small, it will not scale ever. Because the whole problem is that when you apply this analysis and AI ML techniques, you'll be able to automate the correlation part only, meaning that you'll be automate a lot of the manual tasks that humans are doing today to keep these systems up to date. But the systems, when you automate, they won't be able to find out causation. So correlation is not really a causation, and that could lead to trust deficit in the remedies, and that could really create a big problem for adoption of this kind of services. So why trust is so important? So if you look at today in communication service provider systems, the operators or the humans are trained for several years and they apprentice for several years because there are thousands of parameters on thousands of different management and other planes. Those parameters and those combinations has to be learned gradually over the years. So if we give those knobs to the machines to turn, then there will be question asked, right? That what happened, why it happened, what should we do about it, what could happen next, and what should be done to take care of this situation. So today, as I said, humans are uh, able to answer those things because they have understood, they have spent decades, and they know their system very well. So now, when we want to transfer all that tribal knowledge and experience into machines or to automate things, it is a big challenge here. And the reason is that causality. So here is the key requirement. If you want to really automate for complexity, and if we want the adoption of that automation, then it has to be trustworthy. So the biggest impediment to that trustworthiness comes really from the causality. So let's look at what I meant here. So I'm going to use this simple illustration here to explain the basic concept of causality, and then I'll go into specifically the communication systems area. So here, as you see, if on the top picture here, if you see or if we observe in the system that temperature started going up, and then if we observe that we saw the fire happening, then we can establish that increase in temperature caused the fire, and in that situation, best course of action is to turn the fan on, which will bring the temperature down and eventually douse the fire. On the other hand, if we observe that fire started first and then we saw increase in the temperature, then we can establish that fire led to the increase in the temperature, and the best course of action for that one is to put a lid on the fire, which will put the fire out, and then eventually temperature will come down. So this is easy to understand. But let's say what happens in this kind of complex systems which I described happening because of these emerging intelligent automation application patterns. Let's say we see that fire the temperature is going up and fire is starting, but we didn't know that what was preceding event. So for example, we saw the temperature rise and then we assumed that the temperature rise led to fire, but we were not able to establish the right sequence of event. And if we put the lead on as an action, then what happens? Temperature will keep going up and fire will keep growing. Even the worst could happen if fire really started first and that led to increase in temperature. But if we couldn't ascertain, especially with the automation systems where humans are not involved, then if we take the action of blowing the fan over it, it could really become disastrous. It could worsen the fire and temperature still keeps going up. So identifying causality basically requires the sequence of event has to be traced across both north-south and east-west in any communication systems. So here, that is the key problem here. So especially if you look at the telecommunication networks, we aggregate lot of performance measurement data over an 15-minute to 1 hour interval, depending on which vendor systems you use. So once you aggregate those millisecond level changes happening in the radio networks or any wireless systems, then when they are aggregated over 15 minutes, for example, on the link adaptation, 900,000 adaptations happens in about 15 minutes. So meaning that when you look at this aggregated data, then you will not be able to figure out whether increase in temperature led to fire or fire led to increase in temperature. So that's why today the way networks are managed is we create these test labs and test networks to ascertain that actions are not going to really exacerbate the situation uh, if it cannot fix it. And that's why, as I mentioned, it requires decades of experience and training. And now we want to put all those things in the machine learning algorithms, and that creates that challenge. So let's look a little bit deeper into that challenge. So as you can see here, in the communication network, when we see a lot of symptoms like drop calls or low throughput or high latency, then there are already corresponding radio compensation mechanisms are already there, which like tries to compensate reactively. But if you try to like look at that, what led to those degradation in throughput or latency or call drops, that is basically a signal to noise ratio. So when signal to noise ratio goes low, that is kind of a root cause. But that root cause has multiple effects, as you can see here. And then if it not fix that root cause, that what started that signal to noise ratio degradation in the first place, then what happens that each individual call in this neighborhood starts to compensate by using different compensation mechanisms, and those compensation mechanisms creates unwarranted interference for all the neighboring calls. So no compensation mechanism comes for free. So if one call tries to compensate, it creates interference, which leads to lower signal to noise ratio for other calls, and then prompts those other calls to start compensating. So this is basically what is happening in the communication systems, any shared communication medium like wireless here. So today, if we want to really manage this increasingly complex next generation communication system, we should be able to identify the root cause, that what started the degradation of wireless communication system in the first place, and then try to address that root cause with the right course of remedial action. And then this problem of blindly shooting with different compensation mechanism may not happen. And this problem really, if you look at from the business terms, the spectral efficiency when it goes down, then the overall capacity and user experience of the system goes down. And as you can see, the whole billion spent on the spectrum as well as the capex put in the building this kind of systems won't become profitable if it cannot support the user experience and throughput. So this is just one part of the communication system I have highlighted, but when you extend it beyond the radio networks up to transport network and this kind of a different compute stacks for edge computing and other public cloud scenarios, then you can think the complexity of the system. that causality has to be traced across east west and north south both. Otherwise, we will just barely be able to automate what humans are doing today, and that is not enough for next generation communication systems. So, how do we solve this problem? So, apparently, we need to look at AI/ML itself to help with the problem those AI/ML workloads are creating here. So, the traditional way of applying AI/ML today is kind of outside in, meaning that we look at one symptom, as you see in this picture here. The doctor is trying to listen to the heart murmur, and when you look at the one symptom and then try to diagnose the problem based on that one symptom, then we are missing all other symptoms. So, meaning that if we want to go from correlation to causality, then we need to really look at active inside out diagnosis, meaning that analogically we have to look at, let's take a human body as example, like physical signals, thermal signals, electrophysical signals, as you see here. And some are actively monitored, and others are uh, passively, or whenever some kind of causation is identified high level, we try to do more testing and more analysis to identify deeper symptoms. So, what we have identified is that this outside in way of applying by collecting the data from data sources and aggregating them and over time period, that will just give you correlation. And for next generation systems, it won't be enough. What we need really is how we can bring it outside in. So I think that's all about the next generation communication systems and AI/ML, how it is going to impact it. Thank you for your time and appreciate your talk. If you have any questions, you can reach out to me on LinkedIn, and my email address is already there with the host. Thanks. Bye bye.